Hi, this is Collin Knowles. I'm going to give a demonstration of my operating system's Project 1. And to begin with, I'm just going to show that I'm in the WSL terminal, so the Windows subsystem for Linux. I've already CD'd to the correct directory, and I've done a command to show that I have the latest version of Rust running right now. And so for the first phase of the project, just going to open up the code there, get that going. We'll go ahead and compile the first phase on my first branch, and we're going to go ahead and run it to show you some concurrency. So in this first phase, what we do is we spawn 5 separate threads. Each thread has shared access to a single resource. In this case, it's a vector, the recipe vector. Each thread is going to be writing an ingredient to that recipe vector. Right here it shows that they have acquired the lock when they're adding it, and then we have added to confirm that the thread has completed its operation. So if we go to the code, here we go, just to demonstrate real quick what I'm talking about. We have that shared resource with the arc pointer, mutex locks for resource protection, the ingredients. Here's every thread being spawned for each ingredient. We have a clone so we can access that pointer within scope. We have a sleep right here to kind of encourage concurrency, make sure every thread isn't moving too fast. They're working at the same time. And then eventually we push threads to a thread, just a standard vector, and we go through that vector. We confirm that every thread has performed its operation. We get the OK on the join and the unwrap, and then we print that final recipe after that it's been made from accessing the values of the original recipe vector. All right, and so that's for phase 1. That demonstrates some concurrency and some thread operations. So if we move on over to Project A, phase 3 through 4, sometimes you got a stash. I think it's the debugger adding a little something new. So in phase 3, we're just going to go ahead and compile, and we're going to run that. So in this case, this section of the project is divided into a deadlock scenario and a normal scenario where we've resolved similar deadlock that was happening in the beginning. So what's going on here is that we have 2 different threads. They have access to 2 different shared resources. It shows when they're attempting to get the lock, when they got the lock, and when they're adding ingredients to that shared resource. The issue here is that thread 2 is trying to lock the recipe, and it cannot do that because there is a circular wait scenario here with the ordering in which these threads are attempting to access that shared resource that creates the deadlock. Also, there is a sleep timer that ensures that happens at least once. If I were to run this several times, what you would see is that eventually we get deadlock from both threads. But for the purpose of this demonstration, I'm just showing that we get deadlock here. So yeah, and then you'll see in the normal scenario, everything works as intended. We get the desired resources printed out that were written to the shared vectors. And just to go into the code here, You'll see what I'm talking about. Much like the other example, we've established them in the same way with the arc, the mutex. For thread 1, we spawn it. We get that clone. Once you've established the lock, which this will 100% of the time, it's the first thread to do that, it will push to that point in memory, and then it will sleep, essentially guaranteeing that thread 2, once it spawns, will grab that lock first, and then thread 1 will attempt to get it. It will fail, and we'll get this error message. We do that using the try lock method, so that deadlock is averted in this case. If I were to do this with a regular .lock method, it would be waiting for an eternity, but we're not doing that. So with thread 2, it's a similar story. In the other section where we've resolved the deadlock, that is twofold. The first method of doing that is that we have ordered them correctly. So there's no circular wait and there's no circular hang. It's sequential. They try to, thread 1 accesses recipe, drops it. But also we have this timeout method. And this timeout method is especially useful because it guarantees that, one moment. Sorry about that. This timeout method, essentially, when a thread tries to get a lock, it doesn't wait forever. Instead, it sets this timer here, and if the thread can't get that lock within that time limit, it'll give up, and it'll stop trying to get the lock. And then, essentially, that timeout just prevents the deadlock situation. And, a thread can occasionally fail to complete its task if it can't get a lock in time. But this is a good way for the program to avoid freezing due to deadlock. So, and you'll see here the result. You get the OK, confirms that the mutex guard has been acquired, and then it allows the push to happen. So moving on to the next section. So now you'll see that I've opened up my Project B branch. This has 2 different programs. Those programs are going to communicate to each other through pipes. So first, what we're going to do is we're going to compile those. Real quick, let me compile that again. Oh, I'm sorry, they're already compiled. So we can just go ahead and run it. There we go. All right, so you see that output 1491625. Let's go to the code and see what happened there. So with generate numbers, what we're doing is we're generating just a list of numbers, and then we're writing them out as standard output. What this is going to do is it's going to write to the buffer that is provided by that pipe. And then square numbers is going to read that in through IO buff reader. And with that, it is going to be able to square each one of those numbers. At first, it parses it into an integer. They're originally written as a string. Then it does that. It performs an operation on what it's read, and then it prints them out sequentially. And so that is my demonstration. Thank you for listening.